All right, so again, let's here. Let's consider. Oops. Let's consider, say, m by n system of linear equations. And as you may recall, in its general form is the following: a11x1, a12x2 plus a1nxn equals b1, a21x1 plus a22x2 plus a2nxn equals b2, and so on up to am1 x1 plus am2 x2 plus amn xn equal bn. So again we have, we have n variables, x1 through xn, and m equations. All right, so the goal for now is to solve the system of linear equations. Okay, and the idea of doing that is to reduce, or say simplify, the system by eliminating variables to the extent that the solutions to the resulting system can be described in some sense or directly, and we will be more precise about that when we get to the point. So the main goal here is to simplify the system by eliminating variables. And what we're going to do to achieve this is to use method is to use some basic operations or elementary operations. Okay, and there are three such operations. One, so before getting to, that's okay. So the first elementary operation would be interchanging two equations, right? I mean, you got m equations, I mean, listed in some order. I mean, you can interchange them. You can interchange any two of them, and the resulting system will, still be, as you can see, pretty much the same system. It's just the ordering of the equations are changed. Now, the second elementary operation is multiply an equation by a non-zero constant. Non-zero, yeah. Or called scalar. Okay. We'll see in examples what we mean by this, but it's pretty clear by the words, by the look of it, what it means. You take one equation, say this one, and you just multiply both sides of the equation by a number that is not zero. And that's what it means for this. That's what the second operation is. Third operation is to add a constant multiple of one equation to another equation. Okay. I mean, again, this is just the meaning of this is just exactly what it says here. You take one equation, you multiply it by a number, and then you add the resulting equation to another equation. Okay, we will see how this works in some examples, but before we proceed, we should introduce some notation for these operations. So let's use this. So we're considering, say, the i's and the j's equation, and the symbol EI here represents the i's equation, the symbol EJ here represents the j's equation, and this two-sided arrow here just means interchanging the two equations. So this symbol here, this notation here means interchanging the i's and the j's equation. Okay. And the second operation is about multiplying an equation by a non-zero scalar. So let's say we have the i's equation represented by EI, and there's a scalar called K. And then this symbol KEI here represents multiply the i's equation by the number K. Okay. Now, lastly, so we would have we sometimes do take, say, the i's equation EI and take the j's equation EJ multiplied by a number K and add the resulting equation to EI. Okay, so that this symbol means add the K multiple of the j's equation to the i's equation. Okay. All right, so these are what we're going to use. These are the operations, and these are now what we just saw are the symbols used to describe these operations. Now let's look at how these operations can help us understand solution, finding solutions to linear systems in some examples. Okay. So let's say you have x1 plus x2 equals to 5 minus x1 plus 2x2 equals to 4. And keep in mind, on the side here, keep in mind is that the goal of using this, performing these operations is to eliminate variables. Okay. Now in this example here, you have two variables, two equations. So what can we do? Our goal again is to eliminate variables. So let's say, what if we just take E1, add it to E2? Okay. So that keeps the first equation the same. Now the second equation becomes the sum of these two. So that will be, here will be a minus x1 plus x1. That will be 0. Oops, sorry, this is x2. And over here, you will have x2 plus 2x2, so 3x2. That's equaling 5 plus 4, that's 9. Okay. So now what happens next? Now if you look at the new system, in the second equation in the new system, from here, I can immediately read off the value of x2. Right, the first equation remains the same, but if I look at 3x2 equals to 9, I see that x2 equals to 3. Okay, that's the value of x2. So what do you do now? Sorry, once again, let me erase this. Now, if you, again, keep in mind that the goal is to eliminate variables. Now that you have the second equation here telling you exactly what x2 is, you can use this to eliminate the x2 in the first equation. So that operation we need is subtracting the second equation E2 from the first equation E1. And that will give us, second equation remains the same. Now the first equation still has x1, x2 is gone on the left hand side. The right hand side is 5 minus 3, so that's 2. Now that's telling us x1 is equal to 2, which is the goal which we are aiming for, right? Finding the values of x1 and x2. Okay, so that's one example of how things are done. We can do, let's do one more example. So this is the first example. Say second example. Let's consider a more complicated case. 2x2 plus x3 equals to minus 2. 3x1 plus 5x2 plus minus 5x3 equals to 1. 2x1 plus 4x2 minus 2x3 equals to 2. All right, so what do we do here? What do we want to do? Again, the goal is to eliminate variables. So which one would be easy to eliminate? And this is E1. This is E2. This is E3. So if we do, so let's see right here. If we do E2 plus 5E1, right? That will be the following. E1 stays the same, 2x2 plus x3 equals to minus 2. Now, E2 gets add 5 copies of E1, but E1 doesn't have an x1, so 3x1 is still 3x1. Now I got 5 copies of E1 from, I got 5 copies of E1 as 10x2, and I have 5x2 here in E2, so that's 15x2. Now, the reason for doing a 5 E1 adding to E2 is because now that 5E1 would have 5 copies of x3, canceling the negative 5 x3 in E2. So that makes x3 0. Now over here, I have E2 plus 5 copies of E1. So that's 1 minus 10, negative 9. Okay. Now let's do this slightly faster. Let's do the next thing. Let's take E3 and add 2 copies of E1 to it. Again, E1 doesn't have an x1, so 2x1 remains the same from E3. Now I take 2 copies of E1, which would give me 4x2, adding to 4x2 from E3, that's 8x2. Now, again, the choice of having 2 E1s added to E3 is because E3 has negative 2x3 and 2 E1 have 2x3, so that will cancel. Then I'll have, what is this? 2 plus twice of negative 2. So that's 2 minus 4, negative 2. Okay. So now what have I done? Hold on. So now over here, I see that these 2 equations no longer has x3. So these 2 together are just 2 equations in 2 variables. So I can proceed to I've succeeded in eliminating 1 variable, and I can proceed to eliminate 1 more. Let's see how I'm supposed to do this. So say, let's try to do E1 minus 2 or 3/2 of E2. Okay, sorry, this is not E1, this is E2. This is now the new E2. This is E3. This is E1. E2 minus 3/2 of E3 is what I want to do. Now E1 is now left on the side for now. E2, if I take E2 and subtract 3/2 of E3, I would cancel x1, right? Because 3/2 and 2 here, that gives me a 3. And so that will make x1 disappear. Now x2 is a different story. So I have 15x2 from E2, and I'm subtracting from it 3/2 of 8x2. Okay. Now on the right hand side, I have negative 9 from E2, and I'm subtracting from it 3/2 of negative 2. And let's keep E3 for the moment. 2x1 plus 8x2 equals minus 2. Okay, so now I have to simplify this, of course. What do I want to do? Hold on. This whole thing gets simplified to, oops. What is this? This is 4 times 3, that's 12. 15 minus 12, that's 3. 3x2 equals, this is negative 9. Right, this is negative 9 minus negative 3. So it's plus 3. So that's negative 6. Okay, so the second equation now becomes 3x2 minus 6, which tells us x2 is what? Minus 2. All right. Now, once we have x2, we could go back and use these other equations to get the values of x1 and x3. So let's say E1 minus 2 E2, right? This is the new E2 now. X2 equals to 2 is the new E2. So if I do E1 minus 2E2, what was E1? This is E1. If I do E1 minus 2E2, I'm getting 2x2 plus x3, well, equaling minus 2. Well, then I have 2x2 equaling minus 4, and I'm taking the difference, right? And that'll give me x3 equals to minus 4, minus 2 minus negative 4. So minus 2 plus 4 is 2. Very good. Now finally, if I do E3 minus 8E2, I'll get, what do I get? I get E3. E3 is 2x1 plus 8x2 equals to minus 2. E2 is x2 equals minus 2, so 8x2 would equal to minus 16. Right? And I'm subtracting this, so that'll give me 2x1 equals to 16 minus 2, that's 14. So x1 is 7. All right. So that's the end of this. And we see, I mean, the steps are not hard. You know, you got various, we've seen various steps of elementary operations being used here as I'm highlighting. And in the end, we found the solution. Very well. This example also shows you a little bit, give you a little bit of idea as to how complicated the process can be, but it's not hard. All right, now, but we want to now do some more general discussion. All right. You see, as you recall, n by n system correspond to n by n, well, n plus 1, say. So n by n system correspond to matrices. Let's say, put it this way. Right? So the n by n system that we had, this one, still a1n xn equaling b1 and so on, am1 x1 plus amn xn equaling bn. This corresponds to the two matrices that you get out of this. One is the augmented matrix, which consists of basically arranging all the numbers in their correct location. So, and finally, the left-hand side, B1, B2, Bn. All right. So this is the augmented matrix associated or corresponding to the system. Now, if you just have this side, the left-hand side will give you a the left-hand side will give you an n by n matrix. That is the coefficient matrix. Of this system. Okay, so now the point I'm trying to make here is that when you try to do operations on linear systems, you can do them, or those operations on linear systems give rise to corresponding operations on matrices. Let's write this down. Operations on linear systems give rise to operations on matrices on the okay, more specifically, as you can see, I mean, the equations correspond to rows of your linear system. Sorry, the equations of your linear system correspond to rows of your matrix. So these elementary operations that we've seen before on linear systems give rise to row operations, what we call row operations. On matrices. Okay, and that's what we can describe now. Let's see here. Row operation. And there are three such things. Again, let's use R to denote row. So Ri will be, let's say, the ith row. Rj is the jth row. And this symbol here means we interchange the ith and the jth row. Okay. We can also do this, take the ith row, multiply by number k. Multiply the ith row by a number k, and we insist that k is not 0. And finally, we can do just like the elementary operations for linear system. We can take, say, the ith row, or take n, the jth row, multiply the jth row by k, and add it to the ith row. So add the k multiple. Sorry. The jth row to the ith row. Right. So these are the operations that we can use. These are the operations, or the row operations on matrices that came from operations on linear systems. And as you can see, the correspondence between linear systems and the matrices is just easier, and it's just simpler to denote the linear system by its augmented matrix. And we could also therefore denote the process of simplifying or reducing a linear system using elementary operations as performing row operations on matrices. So we can describe the process of reducing a linear system linear system by elementary operations via performing row operations on augmented matrix. Okay, let's see. Let's see if we want to do an example. Well, we will be doing examples later, so maybe let's not do that now. Instead, let's think about what we're trying to do. Again, the goal is to solve the linear system. Right, so we start with the linear system. So we start with right. And like I mentioned here, we're gonna try to describe the process of solving the system by working with the augmented matrix. So let's first perform that. Go to instead of keeping track of the system, let's work with the augmented matrix. Okay, And now the next thing to do is to I don't know why that happened. The next thing to do is to perform row operations. And keep in mind that this row operations correspond to elementary operations on linear systems. And the goal of choosing this operation, I mean, you have to choose what operations to perform, in which order, and the reason for your choice would be to produce a simplified system or a simplified matrix that you can, from which you can read off the solution. So the resulting thing, let's call, I mean, after performing these row operations, you're going to get a matrix. Let's call this matrix a reduced matrix. And then you convert it back to a system of equations, reduced system of linear equations. And then you read off solutions. Okay. Now, okay, so this is the plan, a general plan for solving linear systems. And the key step, of course, is this row operation. You have to choose these row operations so that you produce a reduced system from which you can read the solutions. The way we choose this operation is to keep in mind that the goal is to eliminate variables. Eliminate variables. Okay, and there are certainly some rooms of flexibilities here, but for now, let's talk a little bit about another issue. So first of all, there's a concept here. When we do these row operations to do these elementary operations to our linear system, we've changed the systems. The equations look different. But they do nevertheless have the same set of solutions. And the concept to be introduced here is that two systems of linear equations, are what we call equivalent. Equivalent if they have the same set of solutions. Okay. So basically the point is, key point, elementary operations produce equivalent systems. Okay, so we don't have to worry about performing these operations, well, because they'll keep the solutions the same. So we can really freely perform these operations with the, if it does help us simplifying the system. Okay, but now let's consider another thing. That is this step. Right, this step is supposed to mean this, right? You have a reduced system of linear equations, and you just somehow see the solutions to the systems directly. So the issue to be raised here is, how are we going to do that, right? So you should ask how to do this. But more precisely, the question to be asked should be, what do we mean by a reduced system? How reduced? We can certainly eliminate variables one after another, but just how reduced should the system be before we know that we can stop and start looking at the solution, looking for solutions? So to put it this way, how, quote, reduced do we want the system to be? In order for us to resolve the solutions. Okay, and again, we're going to use the correspondence between systems of linear equations and augmented matrix to do this discussion. So the answer to this question is, we want it to be in what we call echelon form. Echelon form. Okay, so let's make that definition. The definition actually is for matrices. Okay, so let's say an m by m matrix, call it B, is in echelon form. Echelon form highlighted if the following happens. 1. All rows that consist entirely of zeros are grouped together at the bottom of the matrix. In other words, 0 rows are in the bottom. Now, in every non-zero row, the first First count, and when you have a row, you count from the left. Counting from the left. The first, when we have a non-zero row, it's going to have a non-zero entry somewhere. That's what a row being non-zero means. And the first such non-zero entry, first non-zero entry is a number 1. Okay. Third, now if the third condition is this, if the if the I plus if the I plus first row contains non-zero entries, then the first non-zero entry is in a column to the right of the first non-zero entry in the ith row. Let's first write this down. Okay, so let's now see this in a picture. So let's say this is the ith row. Oops. This is the 0. There's a 1 here. Something happens. Let's say this is the ith row. Now the next row, right? The next row will be the I plus first row, and this row could, it could be entirely 0, right? Because it's possible it could be one of those 0 rows, or maybe it's a non-zero row. Then it's got some non-zero entry somewhere. So it starts with 0 maybe. And the requirement 3 that I just wrote down is that the first non-zero entry, in this non-zero row, the I plus first row, is going to have to appear to the right of the non-zero entry on the ith row. Okay, to the right. Now, this is just saying that things like these can happen. If this is the ith, this is the I plus first. It's just saying that the first non-zero entry 1 here cannot happen to the left of these other 1. Okay, this is not allowed. All right. So we'll see some examples of this later on. But let's continue with the definitions. And there's one more definition. This is the definition of, this is the description of what we mean for an n by n matrix to be in echelon form. Now, it's even more restrictive situation. definition. A matrix that's already in echelon form is in reduced echelon form. Okay, reduced echelon. Reduced echelon form. If something more happens, if the first non-zero entry in any row is the only non-zero entry in its column. Okay, what am I saying here? So let's draw an example. Let's say you have a non-zero row, finally having a 1. Okay, and this 1 here, this 1 is a non-zero entry in a row, in this row, say. And the requirement that we have here for being in reduced echelon form is, now if you look at this column, the column that contains this 1, the requirement is that everything else, all the other entries in this column must be 0. Yeah. Okay, it's just this. If in a row you have a non-zero entry, then the column containing that non-zero entry contains only one non-zero entry. Put it differently. Okay, now examples. All right. So say 1 minus 1, 4, 3, 0, 0. No, I want it differently. 0, 1, 6 minus 5, 0, 0, 0, 1. Okay, so what is this? This one is in echelon form. Right? I mean, let's examine this. I mean, there are 3 conditions. I cannot really redisplay them. But so the first condition is about 0 rows. This one doesn't have any 0 rows, so that's okay. That condition is automatically true. Now the second condition is that if a row is not a 0 row, then the first non-zero entry counting from the left is a 1. In this case, the first row is, well, obviously not a 0 row, and the first non-zero entry is a 1. Likewise, the second and the third row. And lastly, the last condition is about the first non-zero entry sitting towards the right of the first non-zero entry of the previous row. Right, so that condition has nothing to do with the first row. But for the second row, the first non-zero entry is here. That's to the right of the first non-zero entry of the first row. And similarly for the non-zero entry on the third row. Now, as you can see here, this is not in reduced echelon form. Because because the condition isn't satisfied. Right over here, in the first column, the first non-zero entry in the first row sits in the first column. That has only one non-zero entry. That's fine. But the first non-zero entry of the second row sits in the second column. That has other non-zero entries. And the first non-zero entry of the third row sits in the last column, which also has other non-zero entries. So the condition just fails miserably. Never mind, that happens. Now, one more example. Say 1 0 0 0 1 0 0 0 1 2 minus 1 3. Now, this is in this I claim is in reduced echelon form. Okay, again we have some conditions to check. Again, the first conditions is about 0 rows, and this matrix has no 0 rows, so that's fine, automatically satisfied. The second condition is about the first non-zero entry in any given row, and the requirement is that those things being 1. And indeed, that's what we see here: 1, 1, 1. Now, and the third condition is about the first non-zero entry of the lower rows sitting towards the right of the first non-zero entry of the upper rows, right? Look at it again. That's what it means. And this certainly holds for this example. The ones, as you go down the rows, the first non-zero entries move towards the right. Now, for being reduced, you need the columns containing first non-zero entries to be, to be simple enough so that there's only one non-zero entry in that column, and that's indeed the case in this example. Very well. Okay. So now that we've introduced this notion of reduced echelon form, or just echelon form, the next goal is to, or rather the plan, the way of solving linear system is to change the augmented matrices to reduced echelon form. Using row operations. Okay, we will do some examples in the next lecture, and we will see in those examples immediately why being in reduced echelon forms will help you read our solutions. Okay.